Right, moving on with Module 10, reflection. We are going to review some of the things we talked about in the previous lecture and go through some examples. So we introduced this idea of the law of reflection, where if you draw a perpendicular line or a normal to the surface, that the incident angle is going to equal the reflected angle. And we talked about the fact that you can bounce light off of different surfaces, and we investigated some effects that can occur due to that. But right now I'd like you to think about a more fun example where you can imagine yourself at the entrance to a hall of mirrors with a laser pointer that you wish to reflect in such a way that you can go around this corner here. Okay, so what you start off with is a laser beam pointing something like what you see here. What happens when it gets reflected is that it bounces like so, and then back at you, ending ultimately to your left. So if you want the laser beam to make it around the corner, what do you need to do? You're going to have to change the angle of incidence somehow. The question is, are you increasing or decreasing the angle of incidence? Now remember that the angle of incidence is measured from the normal. So if I am decreasing the angle of incidence, I'm making this closer to that perpendicular and further away from here. Okay, so let's imagine that you decide to decrease the angle of incidence. By decrease, again, I mean that because this is our normal, our perpendicular, you've now made this angle shallower and this angle shallower and this angle steeper. And so if you do that, you find that again it bounces off of this surface here and then back at you, but now it's landing somewhere to your right. So you do this again at another even shallower angle with respect to the normal. If this is your normal, we've decreased this angle even more. And like before, it's going to bounce off of this surface and back at you again. Now it's landed in such a way that it's hitting here. So we want to bring this all the way up to this corner so that it can bounce off of here and so on through the Hall of Mirrors. So we still have further to go. Let's say that we finally find this magical spot where the angle is just right so that when it bounces off of here, it just barely hits this corner, and then it's able to proceed through the house of mirrors, bouncing off of each side and get around that corner. Now, given everything that you see here, this would be the bare minimum that you need to get it around that corner, and based upon the measurements here, you can actually find what that angle is that's required. So to start with, if this is the entire length here, and I am told that this is 1 meter from the corner, then that allows me to determine that this distance here is equal to the 2.8 meters that you're seeing here. Now, based on some properties of trigonometry, I can find something out about these angles. So, for example, this angle here, I'll call this theta 0. The tangent of that angle will be equal to the opposite over the hypotenuse 2.8 that we just talked about. In fact, let me write it up here so it's easier to see. Okay, so the tangent of this theta will be equal to opposite over adjacent, 1.8 over 1.8 over 2.8. And so when you take the tangent of that angle, you're going to find that it's equal to approximately 22 degrees. Okay, which means then that this has got to be 90 degrees minus that, so 68 degrees. Okay, by the law of reflection, then this angle also has to be 68 degrees. And if I draw a perpendicular to this surface up here, then I can see that I've created a right triangle right here. So I'm back to 22 degrees here, which by the law of reflection then means that this angle also has to be 22 degrees. And you can proceed like this with this kind of reasoning through the entire hall of mirrors and determine the angle at each particular reflection throughout the hall of mirrors. Okay, so that's all well and good. Let's see if we can figure out a question for you to calculate on your own that's very similar. So in this example, I am told that the initial, the initial angle of incidence is 30 degrees. What that means is that right here, this angle is 30 degrees. And I want to know what the very last angle of emergence is. So what is this angle here? We'll call it theta final. Okay. So I'll give you a second. Go ahead and see if you can, you might want to pause the video and see if you can work out what that angle is. Okay, and if you reason through in a similar way that we just did in the previous example, then here's how we can work out the answer. So through the law of reflection, this angle has to be equal to the incident angle, so that's 30 degrees there. I can create a right triangle here, which means that this is 60 degrees. And then this is my 30 again. By the law of reflection, this reflected angle's got to be 30. Okay, which means this angle here is 60. And this angle here is 30 then, because I have another right triangle here. Which means that this is 60. By the law of reflection, this has to be 60. Okay, this one then is 30 degrees. Which means that this is now 60 degrees. And so this theta final is also going to be 60 degrees as it emerges from this alternative hall of mirrors in which you were standing over here initially. Okay, so that corresponds to choice D here. Okay, so going back to this example of a plane mirror that we discussed last time, we talked about the fact that at every point the light emerging from the object is then reflected based on the law of reflection, and that what that produces for your eye is a virtual image behind the mirror by just kind of following this dotted line on the opposite side of the mirror. And as we said last time, whenever there is a virtual image, the sign convention is to give that a negative sign for d sub I, distance between the mirror and the image. Okay? And so whenever these kind of plane mirrors occur, you end up with a virtual image, and it's always going to be upright. So this is not the same as what we experienced with a curved mirror, where we can actually converge the light rays and produce a real image in some cases. So speaking of curved mirrors, this is one way that we can bounce the light to a focal point. The best way to actually concentrate energy in this case would be through the use of a parabolic mirror. We're not going to go into parabolic mirrors in this class though, so let's stick with the model that we talked about last time, which was the spherical mirror. And as we discussed before, you can think about this as part of a sphere. In one case, you will have the reflective surface on the inside of the mirror, and that's a convex mirror. And then on the other side, on the other hand, you can have the reflective surface on the outside, and we would call that a concave mirror. So for the concave mirror, actually I think those are mislabeled in the previous slide, so strike that. That should be the opposite of what it says here. In any case, the concave mirror here that you see has got a focus that again is half of the radius of curvature. We talked about the terminology of the principal axis, so it goes through the center of curvature. And for the convex mirror, you have a focus here, again half of the radius of curvature. It's just that now you've got the reflective surface on the opposite side. Okay, and the convention to use for the signs of these different mirrors, we talked about last time. For the concave mirror, your focus is going to be greater than 0, and for the convex mirror, you're going to have a minus sign, so that will be less than 0. The reason for that is that we're basically looking at where the focus is. Is it in front or behind the mirror? Okay, but either way, it's going to be an absolute value of half of the radius of curvature away. It's just that we get this minus sign for the convex mirror. And then at the end of the last lecture, I introduced the mirror equation to you, and we talked about the different sign conventions to use. Notice that the focus of the mirror is defined as the point where the image would form if it was infinitely far away. The reason for that is, if you think back to the schematics that we drew, where we had parallel rays coming in and then bouncing off, we assumed all of these things were parallel. Well, in order for them to be parallel to start with, then the object has to be very far away, so we consider that to be infinitely far away, and that's where we find what the focal length is. Okay, so let's do an example where we actually apply the mirror equation. And by the way, we're also going to need some other pieces of information in order to solve this problem. For one thing, we have to remember that the focal length is going to be half of the radius of curvature. And we do not need a minus sign in this particular example because the shape of the mirror is concave, and so we have a focal length which is greater than 0. And then we also need the mirror equation, that 1 over this focal length will equal 1 over the distance to the object plus 1 over the distance to the image. Okay, so we are given the radius of curvature in this problem right here. This is my R. Okay, and we are given a height. That's going to be useful when we start looking at the magnification, but it's not really useful here quite yet for parts A and B, which are asking me where the image is formed and whether or not it's real or virtual. Remember that whether it's real or virtual will have to do with ultimately what the sign of this DI is. If it's negative, it's a virtual image. If it's real, it will be positive. Okay, so given the information that I have here, I can use the mirror equation along with this to figure out where this image is going to form. Now, one question I often get from students when doing these kind of questions is, do I need to convert from centimeters into meters? And the answer to that is, as long as you're keeping it in centimeters all the time, then you do not need to convert. It's just that then your answer will also be in centimeters. Okay, you just have to make sure that your units agree. Okay, so with that in mind, I'm going to decide to stay in centimeters. So based on this equation here, where I have the focal length being half of the radius of curvature, that means that the focal length in this particular example is going to be 1/2 of the 13.4 centimeters, which means that we're looking at 6 point. Don't know why it keeps doing that. It turns out to be 6.7 centimeters. And then I'm going to take that and I'm going to input it into the mirror equation. And I'm going to solve for the distance to the image. So 1 over 6.7 centimeters minus 1 over the distance to the object, which was given to me to be 12.1 centimeters, will equal 1 over the distance to the image. So it's just the warning that I gave you. It's just like the warning I gave you when we were combining resistors in parallel or capacitors in series, that when you compute this, remember that that's 1 over your answer. You still have to take 1 over that in order to get your actual answer. So if I plug all of this left-hand side into my calculator, I will find a number that looks like this. And I'm being careful to note that the centimeters, the unit centimeters, is in the denominator. That's why I have a -1 here. That's going to help remind me that I still need to take 1 over that in order to find the distance to the image. And so when I take 1 over that value, I will find that the distance to the image is approximately 15 centimeters. And this is positive. This is greater than 0. Which means that not only have I found where the pawn image forms, I've also found whether or not it's real or virtual. If it's a positive value, then that means it's a real image and that it has formed a distance of 15 centimeters away. Notice that we started off 12 centimeters away, so my image is going to form out here. Okay. So then we also had this magnification equation that I had at the bottom of the last slide in the last lecture, in which you essentially are looking to see whether this image that you've found is going to be greater than the object size or smaller than the object size. And so you can find it in one of two ways. You can just take the ratio of the height of the image divided by the height of the object, or you can also take negative of the distance to the image over the distance to the object. If this number turns out to be greater than 1, then you're going to have an object which is magnified to be larger than the original, that image will be larger than the object. If it is less than 1, then it'll be smaller. So I can continue with this chess example that we were just discussing. Remember that this thing is forming further away from the mirror than where the object was located, and I can figure out whether or not it's magnified to be greater than or smaller than the actual object. So if I take negative of 15 over 12.1, then what I find is equal to approximately 1.24. Now this doesn't have a unit to it because I had centimeters over centimeters, so those cancel out. And this is negative. The negative is because it's upside down. That's what this negative means in my magnification. Now if I had gotten a negative value for my image, so that I had a virtual image over here, then the minus of that minus would cancel out and I would get a positive for my magnification, and then that would tell me that it was right side up. Okay, but in this case we have an image which is upside down, and I can figure out exactly how big that image is if I simply multiply this minus 1.24 times the original height, and I find then that this is going to be the absolute value of this is 5 centimeters, so it'll appear a little bit bigger than the object actually was originally. Okay, and so that's it for the second of these lectures on reflection, and we will go into refraction in the next lecture. Thank you.